Hi guys, I'm Agastya. I'm a graduate student in computer science, and in my previous video, I built a rack system from first principles using only Python and reason through how these systems actually work. In this video, I'm going to build a production grade system tackling actual problems that are solved in the industry. This is already going to be a very long video, so I'll quickly go over the functional requirements. That is that we should be able to read thousands of files and maintain a persistent vector database of all the information that we gather. It should be easy to update, and we should have the contextual understanding of the documents with the query, not just word matching. We need low latency, and this is what I'm choosing for the ingestion. I'm choosing Docling, which is an excellent framework for reading different types of documents and creating chunks from it. And then for embedding, I'm using nomic embed text, which is a highly optimized embedding model, and I'm running it in Ollama. I'm using Qdrant vector database, which is written in Rust, highly optimized for running on CPU, and extremely well suited for production grade tasks. It does a lot of heavy lifting. And then I'll do re-ranking using FlashRank. And for testing, we just run a very small model locally on our device using Ollama. And then we'll retrieve relevant chunks from a folder containing many files and see if even a very small model is able to answer very niche questions from a large set of documents or not. This is the code structure, and let's get into the implementation part. All right, so let's get started with the implementation. Uh, Create our folder, rag, production, and I am first going to create. First, I'll create a environment for it, and for managing Python packages, I will use UV because it's much faster than standard prep. And the fastest way to configure an environment using UV is to create a PyProject file like this. So I have one already created for a similar project before. I'll copy it here and let's change the name here. Add some description. So just specifying all the dependencies, all the files we need. We need Docling, Qdrant, Ollama. Ollama Python library is different than the Ollama application we installed. FlashRank and then Torch and Torch Vision are required by Docling. And then I also specify the index because I want Torch specifically from the CUDA link, which will ensure the GPU's supported Torch is installed. And yeah, that's it. And now I save this, open a terminal, and I run UV sync. Um, I'll specify these flags here just for additional safety, and it will quickly install all of these packages. And you can see it's much faster than Python, and it will create, and it's much faster than pip, and it will create a virtual environment here. So that's the first production grade thing I am implementing. See, it installed PyTorch and all of these in real time so fast. And now I'll just to confirm uh, that we are utilizing the GPU. I'll use another file that I have pre-written sort of. Okay, so importing Torch, Ollama, Torch CUDA available, device name, models, Ollama. Okay, and I also print the models. Just activating the virtual environment, and now okay. So we have the list of models that I pulled using Ollama, and yes, Ollama is running. We have CUDA available. This is my GPU. I bought this PC in like 2021. It just has 4 GB RAM. And now I'll start with the main implementation. Let's make a code folder, and inside this, the ingestion file will. Okay, so I'm using document converter here. Read a file, convert it using document converter, and create chunks using hybrid chunker, and yeah, so I'll import those things. And also, and inside the hybrid chunker, we are using a tokenizer. I'll like to use mini LM, which is in sentence transformers. And then just one function which will process the file and create chunks. So this is going to read the file, converts it into markdown. So any format of file we have, we'll convert it into markdown, and then we are going to chunk it. Also, we uh, Docling, it's weird that it supports all kinds of files, but it does not support txt files. So for that, we will have some manual chunking that we will do, and not chunking manually, we will convert it into a Docling document manually. So that's a fallback mechanism. And I will use a pre-written code for this function and then just go over that code. I'm doing this because we will have to write a lot of code for this specific project. So in the interest of not making this video too long, turn process chunks and then okay. So we get the file path and then just we see if the file path ends with txt, that is we have a txt file. Then we just use Python open function, read this txt file, get all of its content, and we pass all of this content into this Docling document classes object, which has this function of adding text into a Docling document. And then, yeah, we add text into a Docling document, we have this document. Otherwise, We convert this using convert function, which is inside this class, which returns us an object of a class which is representing the format in which Docling stores its documents. And okay, it's going slow. And that's it. So either cases, we have this doc which has all of the text in markdown like format. Then we give it to the chunker. It returns us the chunks. We create a list of those chunks here, right here. And then in these chunks, so these are just strings. And with each string, I want to add some metadata for each chunk, which I plan to use later, and it can be used in many purposes. So for example, I can get some heading, which document provides here, and then from which heading is this? From the part of the file it is extracted from, if there was some heading in it, then I can add that heading here. And I want to add the source, the exact file path that is in my storage wherever I'll be running my RAG system. So where exactly is that file located? I plan to use this feature when I use queries like which of my resumes from all of my resumes stored in my system contains this specific project, so that I can select that resume and then use it for a job application. Page number, it's not page number, it is some kind of description, and then chunk ID, quite simple, the chunk number, and returning the process chunks. And that is it for this file. So this is the ingestion file completed. Now the next file we will be writing is the database. Uh, Creating the Qdrant database, uh, if not already present, adding new information to it, and yeah, that's pretty much it. But to create the Qdrant database, I will require embedding the document. And for embedding, we are going to be using Ollama Nobic embed text. And so this file uh, does the embedding using Ollama Nomic embed text model, which we run using Ollama client locally on our machine. And so I'm creating another folder in this, which is APIs. Ollama runs on a client server architecture. It starts at a localhost port in our system, and then our code connects, makes requests to that localhost port thing. So Llama, and to specify the name of the embedding model and the LLM model we are going to use, I'll create another file, config.py, and just naming the embedding model here. And the LLM model, that's not this one. So I'll quickly check which LLM model we have. Yeah. And if you, and in order to get any embedding model you like, you can just write Ollama pull and the name of that model, and you can search Ollama models at their websites. So this is the model I usually use for most of my projects. It sort of gives me a balance between the most advanced and also it's running on my 4 GB VRAM. Now, an LLM model. LLM model I'll use for the demo when I am passing the retrieved things into the LLM chat. And I'm creating this client as Ollama client. I'm not, people can also use just Ollama, but I'm making a client of it so that I can specify a timeout. Just 2 minutes of timeout because in case the large model is not loading on my local GPU, taking more time, I don't want the application to crash. And then so this function is there to generate vector embedding for a text string. Quite simple description. And then, okay, response is equal to client dot embeddings embedding model and prompt, and we return response dot embedding. Yep, that is what we are going to do here. Okay, so I can understand that this client class inside Ollama has this embeddings function, which I believe returns a dictionary object. And in this dictionary object, next to the embedding key is the vector which has, next to this embedding key is a list of floating point numbers, which is the embedding value. And I can also, I'll write the generate response later when we are writing the demo of the LLM. Now, getting back to our database file. So there are a couple of imports that I want to do here, and I'm also extending this from an already existing project that I have. Okay, so from Qdrant client, I'm importing the client and models, and from models I'm importing point struct, vector params, distance, sparse vector params, and modifier. How all of these are used, I'll explain in a while. Before that, in the config file, I need to add some more things. And first of all, we are getting, okay. So first of all, I am adding the location of the data folder, which we are going to look. And just add it as data source. So this location, whatever location. So right now it will just be a folder called data source inside this project. And inside this folder, I will have all of my files, all of my data like PPTs, PDF, TXT files, all of those files. And on them, I'm supposed to do a RAG. Now, Qdrant, I am planning to run this inside a Docker container. And it's usually run on port 6333. So Qdrant again is going to be running as a client server thing. So Qdrant is running on this local port, and my application is going to make requests on the local port. So everything is running locally on my system, but it's still using a client server architecture. The system is making, like my laptop is making requests. It's not relevant. Great. And collection name, rack collection. Okay, the collection name is yeah, it is the name of the database inside what Qdrant will make inside it, and also sparse vector. This sparse vector is going to be utilized as a hybrid retrieval. What we are going to do embedding exactly. So it's the sparse vectors. They are an additional thing that we will implement here. And this database file is also going to be quite long, so I'll extend this also from one existing project. Mm, let's see. Yes. Mm, it's a better name. And I'm also adding a timeout here as well in case the Qdrant, wait, in case the Qdrant is taking time to load in Docker for that. And then I'm writing a function called ensure collection. This function is basically making sure that a database exists just in case a database does not exist. Not present, create it. And in this also maybe a max retries, and for cool. Whew. If not, self.client.get collection name is equal to yes, collection name. Then we can print creating collection file, and then self dot client dot create collection. This is the Qdrant function that is helping us create a vector database here, and vector configs, embedding, vector parameters, yeah, sparse vectors. Okay, okay, and then if return accept exception, if I is less than max tries, sleep, and otherwise else raise the error. Now, absurd chunks, it just means I have a database already existing and I'm adding chunks in it. And I'll just use just copy a function for it and explain it. That will be better. Yes. Okay, so points is, I believe, a pointer to the different indexes inside the database. And for every chunk inside the list of chunks that we have, we are adding to the database, we create a dense vector for them, and then we append using this class class object the ID we create using we create a unique ID for every single chunk that we are adding, and dense is this here, and the sparse vector which we are using here is the BM25. So sparse vector and dense vector, the difference between them is a dense vector is a embedding that is generated from a large language model. Sparse embedding is just an embedding generated on the exact word it contains, the word count. So it's useful for matching the exact word inside a document with your query. And I'll make this function usable with what we have written. Yeah. Just made the ensure collection method to be consistent with the absurd collection method which I'm using. And so yeah, we are getting the sparse vector, this BM25 score, and the dense vector, which is our Ollama embedding. And we are also adding this additional payload in which I am also adding the metadata of that particular chunk so that the file name is also stored with every chunk which we wanted. And if this was successful, then we upsert in the collection. Upsert is already a function. And now a search function in the database. We have a query, and then I would also enable a limit of 50 perhaps. And for the query also, we would have to get a dense embedding, and this, and then for searching, these are all the points in the database. And why it uses points is because it is using an algorithm called HNSW, which creates a graph like structure for all the information that we have, because the ranking is going to be done once you get the query, but we can still create similar chunks in clusters. So that is why these chunks themselves, they are called points, and that's where this name comes from. And now on this collection names, and so just making sure here that my so while searching, I'm also using the sparse vector. So using the prefetch class here. And query. True. And return the response points. Now another very small function to which is helping me make sure that if a file exists, if we have already indexed this file before, then we are not indexing it again. So that creates my database file. So you can see how Qdrant gives us a lot of these functions which are by default helping us in adding to the database and so much. So such libraries are already very helpful for us. Now I think I should initialize the Qdrant already. So for why is it not enabling me? So this is the Docker compose file, or just and okay, I think one of my projects is already using this, so I have to quit that. Okay, so I removed the container and then just I ran this command and this pulled Qdrant here and started it. So now Qdrant is running. And so adding Qdrant was pretty simple. You just have to write this simple Docker file, services, Qdrant, image. Docker takes this image from Docker Hub, container name. These are my local ports where I want this to be running, where my application will look for. And the volumes part, this adds a local folder in my project root, and inside this folder we will save the collections. So every collection is one database. Another thing, uh, you can go to this link here, and this should give you round vector search engine, but then you can just type dashboard here. What? Okay, this is weird. Anyways, not important to our video. Great. I think for the RAG part, everything has been implemented already. So just the ingestion part and the database part. And now one key thing that I would like to add here, it is re-ranking. So even though we are using a very good algorithm for the embedding and we are retrieving similar embeddings of text for every query, the re-ranking part is creating the embedding of the query along with the document. So we are sort of creating the representation of how every word in the query aligns with every word inside in the document, and that provides more granularity over the results. And I'm using FlashRank for it. use this one here and explain it. Cool. So it uses a very tiny model that runs on CPU, and for the purpose of this video, I'm running this simple mini LM model. Although in a lot of production grade applications, it can also be used. Then we convert Qdrant objects into FlashRank dictionaries here, ID, text, and metadata. And for all the results and search results we pass into this function. And then we create a request. This represents, okay, show me, rank. It represents a re-ranking request with a query and a list of passages. Okay, a query and a list of passages. So passages, it just means chunks for us, chunks slash text, and then we just use this re-rank function, which does the re-ranking, and we return the top k. It's 5 for now. And how many I want to return, that is also something I can specify in the config file. Chunking configuration, not chunking configuration. Okay, during re-ranking, and so I can change this whenever I want. And so now we just have to write a pipeline file, pipeline dot. Okay, so now that all of these files are done, we just have to write this file that will combine all of these things. It goes over all the documents in the data. What's the name of this? In the data folder. Gives them to ingestion.py, gets the chunks, embeds the chunks using database.py, stores the vectors in the Qdrant what vector DB, and then takes the user query, embeds it, retrieves similar chunks from Qdrant database using database by search function, and then re-ranks using Retrieval-Augmented, and finally gives the chunks to LLM to get generate answer. Okay, and the purpose of this file is pretty simple, but it has a lot of boilerplate code. So I'll again extend this from already existing project that I have. From core.re-ranking, go to re-ranker, and let's define these in the config.file. Actually, how about getting 50? No, just 20. Class pipeline. and ingestion is equal to ingestion pipeline self dot database is equal to vector database self dot reranker is equal to reranker self dot LLM is equal to Ollama client and then dot db dot ensure collection. This is initializing the database, vector database. And now I'm creating a file, a function that will scan the whole folder and give them scan the data folder and ingest documents using ingestion pipeline, then embed and store in vector database. And it's called index documents, scans folders and indexes them only if they are new. So if the folder does not exist, then we make the folder and we return. And then otherwise, for all the files, we just read all of the files in this folder if they end with these names. These are the type of file we are taking in for now. And if they do not exist, cool. Otherwise, yeah, we can print these many files we have found. And for every file, if it exists, we skip it. That's why we made the file exist function in the database. And otherwise, the chunks are, we process this file using the ingestion pipeline and get the chunks. And if the chunks are there, we just use the upsert chunks method in the database. And yes, it's added inside the database. And the next one is querying function, which is the last function in this file. And again, so it gives the user query, it gets the user query and so uses the search function which we made in our database py, gives the user query and this top k that we want. Then it re-ranks them using the re-rank function in the re-ranker. And then this part is for the LLM dev. And to do this part, we would have to write a generate text function inside our LLM agent, LLM client, which I will do very quickly here. Cool. And yeah, just you can just write, you can just in your code you can just use ollama.chat and then model and then just give it some messages as well. This is the message that you give to the model. Like in this, you can simply just write hello, and this is good enough. That's how you can just use an LLM inside your application, inside your laptop locally. But here we are just giving system prompt, and this is just string manipulation, string handling in Python. And you can enable streaming, and this gives you a generator object. If you enable streaming, this function, this gives you a generator object, and you can iterate over that generator, that iterator, and you can just keep yielding it. So this gives you very good real-time streaming response that usually you see in apps like ChatGPT. Okay, so the metadata and source. These are some things that I already added with every chunk when I created processed chunks here. So I added the file path as source, and that's the metadata here. And this is the prompt. Yeah, professional assistant, and only using the provided context. That's a little bit of prompt engineering here for keeping it. And you must cite the source file name, that is the source field in the context. Okay. Yeah, it's pretty self-explanatory. And so again, some just string manipulation, and then generating answer, and self.lm.generate response. Cool. Um, One thing that is needed is so that I can import from these files, from these folders. Okay. And now this is the last main function. So I'll quickly create a simple UI. Yeah, again, this is just for, I got this from another project, and this is, if name is equal to me, start this agent, starting RAG agent, RAG pipeline, no, pipeline, import pipeline. There is no RAG pipeline in pipeline. Is there a RAG pipeline in pipeline? Yep. And then, cool, this starts this CLI like thing. This can ask it, hi, I am here. Get well. Ask me questions from the files in the folder. Cool. And let's just run it. And yeah. Okay, so we create an agent here, which is this whole RAG pipeline. And for the very first time, I would also like to index the documents, all of the documents inside it. And then I can remove it later to just show the persistence in the database. So I added some documents in this folder. Let's see if nice. 1, 2, 3, 4, 5. 5 files. Great. Cool. I can ask it about, yeah, let me ask it about this project. Okay. About the 3D Gaussians plotting for text reconstruction project. Okay. Yeah, it did outperform text nerf. Oh, great. And what else can I ask it? Let me add another file. So this is like my application for grad school, and it's like 18 page long. So And yeah, so it only checks for new content, and it did not go over iterating any of these again. It's only checking the processing the new document, which is 18 pages long. Okay. And the best part about this system is that you can just run this function. You can just run index documents function, like use a separate file and just run this index document function separately, and like keep it running as uh, you can keep it running as some kind of a system CTL process, or yeah, some kind of a Linux process, like a cron job. Yeah, you can just keep this running like a cron job in Linux, and it will keep on iterating over your folder, keep on adding documents into your database. Okay, so I added my information about my application to some grad school, and I don't go to the school. Um, Let me ask who all provided the LOR for this notification for UC Davis. The LLM is kind of slow because it is. Oh, great. I'm using like 7 billion parameters model, so it takes this much time. But yep, that's pretty much it, I think. Okay, so thank you for watching this video so far. I hope it provided you some value. I'll attach this whole folder. I'll add this on GitHub. Make it a GitHub repository, and you can view the code base, follow along that. I'll also try writing a Medium blog, which you can follow along for a build like this. But the purpose of this video was not to make a tutorial, but sort of thinking in public and to understand how easy and efficient it is, how easy it is to build these production grade rack systems. So many open source libraries are there which are so much easy to use, and you can see all of these files are like 20 to 30 lines of code, maybe just 50 lines of code max. So it is quite easy to implement a very good production grade RAG, and even if you have some very obsolete information in some file, it will be it will just get that, and it runs very good on a very small GPU. Okay, thank you.